Okay, today we'll learn the concept of work, energy, and power. It turns out that to do work, you need energy. Okay, and we get our energy by eating food and stuff like that. Okay, power is the rate at which you're doing work. So you can do a certain amount of work. You can do it in 2 seconds, or you can do it in 10 seconds. When you do it faster, you're doing the work at a greater power. Okay? And now, since to do work you need energy, power also measures the rate at which you're consuming energy. Okay? All right, so we'll learn all this with reference to our bodies. Okay. So for instance, when I lift this cup up, I've done work. Okay. And when you learn this, when you lift an object of mass m through a height h, the work you have done is mgh. Okay. That's the amount of work you've done. Now, we just learned that to do work, you need energy. Okay. So I used a store of energy in my body. Yep. And so also here's another thing. So if you calculate this number, for instance, and let's say you did 100 joules of energy, 100 joules of work in lifting this object. I spent 100 joules of energy. Okay. So what happened? 100 joules of energy from me got transferred to them. Okay. So, and I'm just giving you an overview of stuff. Okay. And so, energy comes in different forms. So, for instance, in my body, energy is stored as chemical energy. Okay. And when I transferred energy from my body to this object, this energy is mechanical energy. Okay? So energy can be transformed from one form to another. It can be transferred from one object to another. Okay? The total amount of energy remains constant. You cannot create energy, you cannot destroy energy. Okay? All you can do with energy is convert it from one form to another, transfer it from one body to another. Okay? All right, so we'll learn all of that. All right, so here's again a quote at the beginning of the chapter in your book. One of my favorite persons here, one of my favorite scientists. I think it's much more interesting to live not knowing than to have answers which might be wrong. So ignorance is better than knowing wrong answers. All right, so you need energy to do work. So when you lift an object up, and if you lift an object up of mass m through height h, that's the amount of work you did. Okay. So you need energy to do work. Now, when you lift an object up, so we'll learn various efficiencies of our body for various processes. So let's say our body has an efficiency of 20%. Okay. What does that mean? If you use up, your body uses 100 joules of chemical energy, it only does 20 joules of work. Okay. What happened to the other 80 joules? It got converted to heat. Okay, so your body is inefficient. It got converted to heat inside your body, and that heat has to be. You'll have to get rid of that heat. Okay, so for instance, if you go for a run, your body is 20% efficient, and you generate a lot of heat. You have to get rid of that heat, and we'll talk about this in one of the later chapters. But you sweat, and when the sweat evaporates, that takes away the heat. Okay. All right, so you need energy to do work. Every bodily process requires energy. Physical work, when you lift an object up, blood circulation. Okay, see, I need energy to get this object moving. Just like that, if your blood is at stationary, when your heart pumps the blood, it pumps it through your body. It needs energy to do that. Okay? Digestion needs energy, sleeping, and even thinking. Okay? So the body is an energy converter, so from an energy perspective. You intake energy by eating food, and the body does one of three things with the energy it takes in. Okay. It does work, it generates heat. So for instance, when you're cold and you want to maintain a constant body temperature, and if you're losing heat, the body shivers and just creates heat. Okay? Or if it has excess energy, you're constantly taking in energy by eating food. And if you're not spending it in one of these things, what do? The excess energy is stored as fat. Okay? You put it in the bank for future use. Okay, so that's what you do. Okay, so when work is done on an object, the object gains or loses energy. Okay, so when you do work on this object gains energy. If 100 joules of work is done on an object, it gains 100 joules of energy. Okay, so if you do 100 joules of work on it by lifting it, it has gained 100 joules of energy. And where did that energy come from? You transferred from you to this object. Okay, so that's what's going on. Energy comes in various forms: mechanical, chemical, radiant, nuclear. These are all different forms of energy. Okay, so there's all different forms of energy. Natural gas is chemical, biomass is chemical, and so on. Wind energy, solar, and so on. Energy cannot be created or destroyed. It can be transformed from one form to another. So for instance, gas, oil in your car, what do you do with gasoline in your car? You burn the gasoline and then convert that into the motion of the car. Okay, so you can transform it from one form to another and transfer it from one object to another. I can transfer energy from me to this object. Okay. In everything we do and everything that happens in nature, energy is only transformed from one form to another and transferred from one object to another. So we're all just moving the cheese around. Okay. The total energy of the universe is constant. All right, so in this diagram, so for instance, this has potential energy there, and as the pendulum swings, that potential energy gets converted to kinetic energy, back to potential energy. Okay. And this will keep going on, this will go on forever if there is no friction. Okay. So this conversion can go on for forever. Okay, so in this case, the potential energy got converted to kinetic energy 100%. This kinetic energy got converted back to potential energy 100%. Do you guys know how efficient your car is? So when you burn gasoline, it generates heat. How much of that heat is converted to the motion of the car? It's 20% efficient. Okay. So for every $5 of gas you put in your car, you get $1 of motion. Okay. And every time you stop, that motion goes out the window. Okay. All right. But so there's more to the story. It gets worse. Okay, so you. All right. So since we're on it, I might as well tell you that. Okay. So what's the point of your car? To get from point A to B, right? You want to get from point A to B. So here I am. I'm going to make it easy simple, I'm going to use simple numbers. Okay, let's say I'm 200 pounds and I get in a 4,000 pound car. My goal was to transport me from point A to B, and I'm transporting 4,200 pounds. 200 pounds of 4,000 pounds is 5%. Okay, so the car itself is only 20% efficient. Of that, I really used only 5% of that. Okay, so 10% of 20 is 2%, 5% is 1%. So this is, okay, whether you understood this or not, here's what we're saying. For every $100 you put in gasoline, you really only got $1 of what you were intending to do. Okay? So that's how inefficient it is. Okay. All right, but we're surrounded by that kind of things all over the place. Okay. So energy conversion. Okay. So any form of energy can be converted to any other form of energy. So your car converts heat to motion. You can convert motion to heat. Okay. Heat to motion is 20% efficient, roughly. Motion to heat conversion is 100% efficient. Okay. So some conversions are more efficient than others. Okay. So that's what we're saying here. All 100% mechanical energy can be converted to heat. However, in practice, heat to mechanical energy conversion is only about 20 to 40% efficient. Okay. So here is a potential energy to kinetic energy, back to potential. This is 100% efficient. Here's potential energy measured is mgh. Kinetic energy, the formula for kinetic energy is 1/2 mv squared. M is the mass, v is the speed of the object. Okay, so this diagram shows you various processes that convert energy from one form to another. Okay, so for instance, solar cells, what they do is they take electromagnetic energy and convert it into electrical energy. Okay. A light bulb, on the other hand, converts electrical energy back to electromagnetic energy. So these are all devices that convert energy from one form to another. Okay. Radiant energy, photosynthesis plants convert radiant energy to chemical energy. And you can take this chemical energy and oxidize it and convert it back to radiant energy. Okay. And so on. Heat engines, your car is a heat engine that converts chemical energy to mechanical energy. Okay. And friction and burning can convert mechanical energy to chemical energy. Okay, mechanical energy. Friction can convert it into radiant energy. So this is what's happening here. Friction is converting mechanical energy to radiant energy, heat, and eventually radiant energy. Okay. So this shows you all the devices we use to convert energy from one form to another. So why do we, okay, so let's talk about this. Here's radiant energy. We use solar cells to convert this energy to that energy. Why did we go to the trouble of doing that? It is energy after all. Why did we convert energy from one form to another? When you do that, it's because electrical energy is more convenient. It's easily transported. You can charge your batteries. The sun doesn't shine during the night. You can use the electrical energy at night for your energy needs at night. Okay? So whenever we do something, we do it for a good reason. Okay? When we convert from one form to another, we do that because that other form is more useful. Okay? All right. So this diagram shows you most almost all of our energy, we can trace back our energy source to the sun. Okay. So the sun sends us electromagnetic energy. Okay. Plants are the ones that intercept this energy. Okay. So plants convert this electromagnetic energy to chemical energy via photosynthesis. We eat the plants, and then that's converted to other forms of chemical energy. And when we do work, we convert that to mechanical energy. Eventually, all that gets converted to heat via friction, and that heat is radiated back as infrared energy. So here is the energy cycle. So all our energy sources, except nuclear energy, can be traced back to the sun, and even nuclear energy is a result of exploding stars from previous generations. Okay. So all our energy can be traced back to stars. All right, so this shows you how to calculate the work done. Okay, so when you push a lawnmower, okay, the amount of work done, W is work, F is the force you applied, D is the distance you moved. Okay, so in this picture, the force is applied in this direction. That's the distance the lawnmower moves, and theta is the angle between the two. Okay. So this formula is the work done when you apply a constant force. D is the distance moved. Theta is the angle between the force vector and the distance moved. All right, so let's see. If you apply zero force, you do zero work. If you apply a force and you do not move, you've done zero work. So for instance, I can push on this wall all day long, and if the wall doesn't move, I've done zero work. And theta is the angle between them. Okay, so you can test it out. If the angle theta, you can use your calculator, is less than 90 degrees, is between 0 and 90 degrees, this guy is positive. Cosine theta is positive. If theta is 90 degrees, cosine theta is 0. Okay? And if theta is greater than 90 and less than 180 degrees, okay, then this is negative. So the point is, you can do positive work, you can do zero work, and you can do negative work. Okay? So for instance, when you want to stop your car, so here your car is moving forward. When you want to stop your car, you're applying a force in that direction when you apply brakes. Okay? And this angle is 180 degrees, and you're doing negative work. So when you want to remove energy from a system, you do negative work on it. Okay? All right, so again, you just have, so let's say if I apply a 10 Newton force and I move 2 meters, and the angle between the force and the displacement is 30 degrees, you do cosine 30. That's how you would calculate the work done. And you can use it. Let's see, what does your calculator say? Okay, so, and if you do this calculation, this works out to 17.3 joules. Okay. So the units for work, the SI units for work are force as units of newtons, distance as units of meters. Cosine theta is dimensionless. It doesn't have any units. Okay, so the units for work are Newton meter, and this combination of units is called a joule in honor of Mr. Joule. Yep. All right, so I said when the angle theta is between 0 and 90 degrees, work done is positive. So this guy is doing positive work. This guy, he's applying a force, but he's not moving. D is 0, he's doing zero work. he's applied a force lifting this object, but his displacement is perpendicular to the force. Theta is 90, he's done 0 work. Okay. In this case, when he's climbing stairs, there's the force, there's the displacement, he's done positive work. Okay. In this case, if this thing is moving down and the force is applied in this direction, there's negative work being done on the back. Okay. Power is defined as the work divided by the time it took to do the work. So faster you do the work, smaller this number, greater the power. Yep. Power has units of watts. Okay, so work is in joules and time is in seconds. Joules over seconds is watts. Okay. So most of you are using energy at the rate of 100 watts. Okay, so most of you are 100-watt bulb. So like 2 of those things, because that's the constant rate at which you're using energy, 100 joules per second. So if you don't want to lose weight, you have to eat on the average 100 joules of energy per second. Okay? And if you eat more than 100 joules per second, you gain weight. You eat less than 100 joules per second, you lose weight. Okay? All right, 1 horsepower is 746 watts. Okay, so a horse can work at that rate for 8 hours. Humans, if you wanted to work an 8-hour day, humans would work at 1/10 of a horsepower. Okay. So that's the safe level at which you can work. So now you know why in the old days we would use animals in the farms. An animal could do 10 times the work that a person can do. Okay. All right, so what this illustrates is if you walk up the stairs, to climb up this distance, the work you have to do is mgh. Okay. Now the amount of work done, whether you're walking up or running up the stairs, is the same. When you run up the stairs, the time taken is less. The time taken is less, and the power consumption is higher. Okay. All right, here's a simple calculation. Okay, so let's say what this shows you is, so this nurse is lifting this child up. That's the center of gravity. What matters is how high did the center of gravity get. Okay, so this is the center of gravity of both the nurse and the child. And when she lifted herself and the child up, the center of gravity went up that much. Okay, so the amount of work she did was mgh, that is the combined mass. G, so the work done is mgh. The combined mass of the nurse and the child in this problem is 75 kgs. G is the acceleration due to gravity. Okay, and the height, the center of gravity rose by 1/2 meter. 1/2 meter is that much, roughly 2 feet. Okay, and this works out to 368 joules. Okay, so this combination of units is a joule, about 400 joules. Okay. All right, so we've learned that to do work you need energy. For various bodily processes you need energy. And where do we get our energy from? We get our energy from eating food. Okay. So here are here's a chart showing you the caloric content of food. Okay. Now, I'll mention one thing. So a physics calorie is the heat needed to warm 1 gram of water by 1 degree Celsius. This is a physics calorie. Okay, 1 gram of water, let's see. Anybody have a bottle of water? Okay, you guys have seen those plastic bottles. A cap full of that water is about 1 gram of water. Okay. To warm that much water by 1 degree Celsius, you need 1 calorie of heat. Okay. A kilocalorie is 1,000 of these calories. A kilocalorie is a food calorie. Okay. That's equal to a food calorie, which is written with a big C. Okay. So that yogurt you buy is 80 food calories. It's really 80,000 calories, 80,000 physics calories. Okay. It's just that it's hard to sell a yogurt if you write 80,000 calories on it. Yeah. So humans, we eat 2,500 food calories roughly a day. That's really 2 million, 2.5 million physics calories. Okay? But anyway, just need to be aware of that. So here we'll use the physics calorie. So a kilocalorie is that much. Okay, so this table gives you caloric content of various foods. So this is 1 food calorie, but that's 1,000 calories. A kilocalorie per gram. So average carbohydrates, breads and pastas and all, have 4 kilocalories per gram. Average protein has 4 kilocalories per gram. Okay? And fat is twice that, a little more than twice that. Okay? So that's the caloric content, and this gives you various caloric content from various foods. Okay. So we eat these foods. When you want to release the energy in animals, the oxidation process is complex and can result in both thermal and energy and work being performed by the animal. If an animal consumes more food than it needs to do work or keep warm, it will convert the excess energy to fat. Okay. And again, like I said, okay, so energy input goes into one of 3 things: work, and since we're warm-blooded animals, we have to keep a constant body temperature. Okay, so thermal and okay, any excess energy that you're not using for the first 2 things, you're storing for a rainy day. Okay. All right. All right, so here's a simple calculation that that's useful to be aware of. Okay, so let's say an average person needs 3,000 calories of food energy per day, okay, to maintain their body weight. And instead, if they eat 4,000 calories per day, okay, so if you eat 1,000 calories extra, what kind of exercise would you have to do to burn that excess those excess calories off? Okay. And this says energy consumption rate for various activities. So for instance, here they use the cycling example. So for cycling, you're using 5.7 kilocalories per minute. Okay, and this is a good pace, and this is about 10 miles an hour. Okay, 5.7 kilocalories per minute. Okay, so you're using 1,000. You have 1,000 excess calories. Okay, and so if you divide 1,000 kilocalories, you ate in excess of 1,000 kilocalories, and you're trying to burn that off, and you're going to burn it off by cycling. So 1,000 divided by that, the kilocalories cancels, and this divided by that is 175. So you would have to cycle 3 hours to burn that excess calories off. Yep. That's what that said. So, and you can see swimming would be a good one too. Climbing, cycling, that's fairly brisk rate of cycling. Whereas running, I don't see running. Okay. All right, so here are various forms of energy. Kinetic energy is the energy in motion. It's 1/2 mv squared. Thermal energy is heat energy. Okay. Potential energy is when you raise an object up. Um, this is potential energy. It's called potential energy because you can release it anytime you want it. Okay. Light energy is energy in electromagnetic radiation, and okay. And this mass energy, you guys probably have all seen this equation that Einstein gave us. This is the energy content of a mass. C is the speed of light. Okay. Now, so from this equation, okay. Has anybody seen the Hoover Dam? Okay. So to run the well, Hoover Dam is 1 gigawatt. Okay, roughly. A gigawatt is a billion watts. Okay, so this bulb is a 100-watt bulb. Okay. So with a gigawatt, you can roughly run 1,000,000 homes. Okay, it's more like 500,000 homes, but we'll say you can run 1,000,000 homes. All right, I'm just giving you numbers. So to run the world constantly, you need 16,000 Hoover dams. In the US, we use 20% of that energy. So to run the US constantly, you have to have 3,000 Hoover dams. 3,000 Hoover dams have to operate 24/7 to run the US. Yep. That's our energy consumption. All right. What I'm trying to tell you is the power of this equation. Okay. You can run the US for an entire year if you could just grab one of the cars in the parking lot, not the big one, a small car, and convert it all into energy. That's how much energy content there is in a mass. Of course, that's very hard to do. That's what a nuclear power plant does. It converts some of the mass to energy, okay, using uranium and stuff like that. So this problem illustrates that point. Okay, so what this is showing you, and again, you just have to have a sense for it. I don't think there's any question on the exam on this thing, but I'm just going to go over it anyway. So E equal to mc squared. That is the energy content of the mass. C is the speed of light. All right, there is the speed of light. So there's 1 gram converted to kilograms. Okay, so there's the energy content of one gram of mass. Okay, again, 1 gram of mass is a cap full of water. You take that water, and if you could convert it all into energy, here's what you could do with it. Okay. So there's the energy content of 1 gram of mass. Okay. So this is an adult. That's their energy content. If humans ran on nuclear energy, we could feed 10 million people with 1 gram of mass for a day. Okay. So that's how much energy there is in that 1 cap full of water. Okay. All right, can energy be created or destroyed? I'm sorry? No. So all you can do is convert it from one form to another, okay? All right, so if this is a frictionless surface, this has gravitational potential energy, and when this slide gets to the bottom, what has happened is it's been converted to kinetic energy. So for instance, here, this has gravitational potential energy, and when I dropped it, it got converted to kinetic energy. Same process happens here. Okay? And what this shows you is, so this calculation assumes no friction. There's gravitational potential energy. and that got converted to kinetic energy. M is the mass of the sled, and so on. Okay, so the speed at the bottom, if the height is 100 meters, 100 meters is a little more than a football field length. Okay, so if you drop an object, I guess in Daytona Beach we don't have any buildings that tall. So twice the height of the tallest building in Daytona Beach. So if you drop a rock from that height, the speed would be 44 meters per second, a little over 100 miles an hour. Yeah. Power calculations, this is the rate at which energy is used, or the rate at which you're doing work. So we'll show you the calculation. You're climbing a flight of stairs, okay? And the work done is, this is how much work you do when you climb a flight of stairs. That's your mass, that's the acceleration due to gravity, and that's the height you climbed, okay? And now the question is, how fast did you do it? Okay. So there's the 60 kg person. 60 kgs is roughly 130 pound person. Okay. So and 2 meters is roughly half the height of this floor, from floor to ceiling. So that's one flight of stairs. Okay. Hi, good morning. All right, so if you climb that in 2 seconds, that's 500 mgh divided by that, that's 600 watts. Okay. And 1 horsepower is 746 watts. So this is converted to horsepower, that's 0.8 horsepower, okay, roughly. So if you climb up that one flight of stairs in 2 seconds, you worked at the rate of 0.8 horsepower. Okay. All right. Some of the best athletes in the world, if you want an intense workout, let's say for half an hour, okay, some of the best athletes can only work at 1/3 of a horsepower for about 30 minutes. Okay. You can work at the rate of 1 horsepower for maybe 10 seconds. Okay, and then you're shot. All right, so the reason we talk about all of this is running up stairs can be quite stressful. So people with heart problems are warned that climbing stairs is one of the most stressful activities that they can perform. But if you wanted to exercise and get in shape, stadium stomping is a very good thing to do. Running up and down flights on bleachers and stuff like that. Okay. Okay, now we'll talk about efficiency. Efficiency is how to get the best bang for the buck. Okay. So efficiency is defined as work or useful energy out divided by work or energy input. So what energy output efficiency is, output divided by input. Okay? In this case, we're talking about energy, or you could do power output divided by power input. Okay? So this works as well because power is work divided by time, and output work divided by time, and input work divided by time, and the time will cancel. So efficiency can be calculated either using this formula, output work divided by input work, or by doing it output power divided by input power. Okay. Okay. So a certain amount of energy is always wasted when people, animals, machines, or electrical devices do work. Energy is never lost, but some energy goes into a form that is not useful work. So when I lifted this object, I'm 20% efficient. 20% went into doing the work, and the other 80% went into heat. Okay? And so I'm only 20% efficient in doing that. Okay? So the wasted energy, it goes mostly to thermal energy. Okay? Okay, so, and we'll talk about this in a later chapter. One method of getting rid of this thermal energy, if you produce more heat than is needed to keep your body warm, you have to get rid of that heat. And is the evaporation of perspiration. Okay, you sweat, and when your sweat evaporates, that excess heat is taken away. Okay. All right, so here's why we talked about all this stuff. Every bodily process requires energy. Physical work, when you lift an object up, blood circulation, digestion, sleeping, and even thinking. Okay. When you're thinking, your nerves are firing, ions are moved in and out of your body, and actually 20%, 25% of your energy is used to place the ions back in where they belong. So your ion pumps use 25% of your energy. Okay. So the body can be thought of as an energy converter, with intake of energy, food being converted to mechanical, thermal, or energy or stored fat. Okay, so here's the efficiencies. Cycling, when you cycle, the efficiency is 20%. Swimming on the surface is 2%. Swimming underwater is 4%. That's why we talked about this. When swimmers start a race, they dive into the pool and they try and stay underwater as long as possible because they're more efficient underwater. But they eventually do have to come to the surface to breathe. Okay. When you're swimming underwater, you're not taking in any more oxygen. So to get energy, you have to oxidize ATP. So you're using all the existing oxygen in the bloodstream. Okay, that's anaerobic exercise. Okay, and you can last for about a minute that way. Okay. So you can do that. Shoveling is 3% efficient. Okay, why is this 20% efficient and this 3% efficient? I'm sorry?
Because the wheels are moving with the light.
Okay, so we'll learn this in a second. The more muscles you use to do an activity, the less efficient you are. Okay, so we'll see that. So keep that in mind. A coal power plant is 40% efficient and so on. Okay. The efficiency of the body ranges from 2 to 20%. Okay, you saw that. So why does the body efficiency vary with activity? The more muscles used to produce useful work, the less efficient the body is. Okay. A single muscle is about 25% efficient. So if you use a single muscle, you'd be 25% efficient if some activity involved that. Okay. So the body can never be more than 25% efficient. Okay. By the way, many organs consume energy and do no work. So for instance, your liver does no work, and you'll see in a second it uses quite a bit of energy. Okay. Leg muscles are the largest in the body, hence cycling and climbing stairs are relatively efficient processes. Shoveling uses arms, shoulders, legs, and back muscles, and then has an efficiency of 3%. So in the shoveling activity, you're using a lot of muscles, and they're essentially working against each other. And in last chapter, you saw that when you use many muscles, your you can apply forces in various directions. Okay? So what is the difference between a well-trained athlete and me? So well-trained athletes are very efficient. Two individuals performing the same physical activity have different efficiencies. The person who has the fewest muscles exerting forces in opposition to one another will have the greatest efficiency. Okay? And so that's why you have coaches telling you how to perform a certain athletic task and stuff like that. Okay? And frequently be able to accomplish the most work for a given amount of energy spent. All right, so here's a problem. The low efficiency of the body means that significant amounts of thermal energy is generated. Okay? And your body is most efficient when the core temperature is 37 degrees Celsius. Okay? And if you produce too much heat, you have to get rid of the heat so your body doesn't overheat. Okay? And so on. So the portion not needed to maintain body temperature must be dissipated into the environment. Q is for heat, so you have to get rid of the heat.
What was that, Q?
Q is heat. That's excess heat that you have to get rid of in the body. Okay? So the metabolic rate, we'll talk about the basal metabolic rate. So let's say you're just sitting there and your body's consuming energy, and like we said, most of us are glowing like a 100-watt bulb, so you're using 100 joules of energy per second to maintain your body. Now, of course, if you go for a run, you'll probably be using 1,200 joules per second. Yep. You'll be glowing like a 1,200-watt bulb. Okay. Right. Now, how do we get energy? So we have stored chemical energy, and to release this chemical energy, again, ATP is the energy molecule, you combine it with oxygen to release that energy. Okay? So a good way to measure your energy consumption is to measure your oxygen intake. Okay? How much oxygen you're using. Okay? So that's a way to measure your energy consumption. Okay? So the basal metabolic rate, so the total energy conversion rate of a person at rest is called the basal metabolic rate. The rate of energy consumption of various organs is shown. Okay, so here is the energy consumption. This is in percentage. This is in watts. So this is for a 65 kg male, which is about 65 kg. Each kg is about 2.2 pounds, so 145 pound male. Is the energy consumption is 85 watts, but to keep it simple, we'll say 100 watts. Okay, you see the liver and the spleen uses about 27% of your energy. Your brain uses 20% of your energy. The muscles, skeletal muscles use 18%, kidneys use 10%. The heart is using 7%. Okay? And so on. So this shows you that. Okay. The human brain, which is pretty amazing. Do you guys know what is the most powerful computer on the planet? Anybody know the most powerful computer on the planet? The thing attached to your shoulders. This thing, okay, some estimates are, you can take all the laptops in the world. This thing is more powerful than all the combined laptops in the world. Okay. And here's the amazing part. How much energy does that laptop use? That's a 100-watt device. Here's a device that's working on 20 watts, and it's more powerful than a billion of those guys. Absolutely amazing. Yeah. All right. The human brain with 86 billion neurons is the most complex energy consuming brain on the planet. Approximately 6 kilocalories or 6 kilocalories are required to sustain 1 billion neurons. Okay? And you have 100 billion neurons. So you need 500 kilocalories. Remember, kilocalorie is a food calorie. So you need 500 kilocalories every day to run your brain. Yeah? So that's half a cheeseburger. Okay. All right. By the way, so if one ate raw food, we'd have to eat 9 hours each day to supply enough energies. So when we cook food, when you cook food, it has 3 times the energy per pound. So 3 pounds of uncooked food, 1 pound of cooked food has the same energy as 3 pounds of uncooked food. Okay? So you're increasing the energy density of the food while by cooking it. Okay? So it was the invention of cooking a million years ago that has allowed the human brains to evolve to the present degree of complexity. And proof of this is a great statement from your book, No Other Primate Cooks. So that's why their brains can get larger. You know? All right, you guys can read this. Okay. Energy consumption is directly proportional to oxygen consumption. Okay. So you want to release, you want to convert your chemical energy to usable form of energy. What you have to do is you have to oxidize ATP molecules. So the more oxygen you're consuming, the more oxygen you're breathing in, the faster you're releasing energy. Okay. Approximately 4.9 kilocalories of energy are produced for each liter of oxygen consumed. Okay, when you breathe in oxygen, okay. So for each liter of oxygen consumed, independent of the food type. Because of this, some physiological measurements use the oxygen consumption rate as a measure of individual's energy production rate. So you might have seen people, physiologists, they'll have athletes run on treadmills and they'll have a measuring device for how much they're breathing and so on, how much air they're breathing. Okay. Here's a couple of numbers. The digestive process is quite effective in metabolizing food. Only about 5% of the caloric value of food is excreted in feces and urine. Okay, so what this number says is when you eat food, your body absorbs 95% of the nutrients. So here's a human, there's the 100%, 95% gets absorbed, and 5% is excreted. We're not able to absorb that 5%, last 5%. Why is that? We'll learn about this later, but why do you think might that be?
It's not digestible.
I'm sorry?
It's not digestible like fiber or.
No. So what we're asking is, no, go.
Is it like unnecessary?
No. All right. If there's a penny lying on the floor, how many of you will pick it up? It's not worth your time. You won't pick it up. If there's $5 lying on the floor, you'll pick it up. So if it costs you more than it's what you're getting out of it, you don't pick it up. Okay. So the last 5%, and we'll learn why this is so. We'll learn about diffusion and stuff like that. Okay. So. During rest, most of the energy consumption of the body ends up as thermal energy. Again, okay, I'm trying to this. Okay, I got 15 more minutes. Do you feel rushed? I'm trying to decide. I want to try and finish this chapter, but I don't want to rush through it as well. I have about 15 more minutes to finish the chapter. Okay. I want to save 10 minutes for the quiz. Okay, so what this problem goes through is how many grams of fat will an ideal person gain in a day by consuming 2,500 kilocalories of food? And what they do is a person at rest consumes 1 kilocalorie per minute. So this is the basal metabolic rate, okay, in those units. Assume all the extra energy is converted to fat. And 1 gram of fat is 9.3 kilocalories. Again, you just have to have a sense for this. You don't have to, but if you're interested in it, so energy is power times time. So remember, power was energy divided by time. So if you multiply that, and energy is power times time. Okay, this is the basal metabolic rate, 1.22 kilocalories per minute. And so if this is the basal metabolic rate, that's how many kilocalories you'll consume per day. Okay, so if you're just sitting on the couch all day long, this person is consuming about 1,800 kilocalories. Okay, and if this person eats 2,500 kilocalories a day, you're eating excess of 700 kilocalories per day. Okay, so 743 kilocalories excess you ate in that day. And 1 gram of fat is 9.3 kilocalories. So if you divide that by that, 80 grams of fat. Okay, so you would gain 80 grams of weight in one day if you just sat on your couch all day. And 80 grams is, how much is 80 grams? A can of soda is about 350 grams. So 1/4 the can of soda of fat you'll gain, of weight you'll gain. Okay, that's what that problem shows you. Did you guys understand that? Okay. All right, this goes into the details of your oxygen consumption. Okay, energy consumption is directly proportional to oxygen consumption. Approximately 4.9 kilocalories of energy is produced for each liter of oxygen consumed, independent of the food type. Okay. A person sitting at rest consumes 20 liters of oxygen per hour. Okay. So here are the details. Average respiratory rate for a person is 12 breaths per minute of half a liter per minute, half a liter each, 12 breaths of half a liter each per minute. Okay, I need to fix that. You're taking 12 breaths per minute, and each breath you're taking half a liter of air. Okay. So this is at the resting rate. So 6 liters per minute. You're breathing in 6 liters of air per minute. Okay. And so 6 times 60 is 360 liters of air per hour. Okay. So you're breathing in 360 liters of air per hour. Air is 20% oxygen, so this would be 72 liters of oxygen. So you're breathing in 72 liters of 20% of that. 20% of this is 72 liters of oxygen per hour. Okay. But only 28% of the oxygen is used. So all the oxygen you breathe, only 28% gets into your blood. Okay, 72% of that oxygen remains in lungs. Okay, and so when you breathe out, that oxygen is coming out. Okay, so The other 72% of the oxygen is exhaled and can be used for mouth-to-mouth resuscitation, blowing on charcoals, and so on. Okay? So CPR and all, if you used all the oxygen you were breathing, you couldn't do CPR. Okay? So that's what that shows you. What this problem shows you is the following. This is the oxygen consumption rate when you're cycling, and this is the oxygen consumption rate when you're sleeping. Okay? And that ratio is about 8. Okay? So what that means is when you're cycling, your energy consumption rate is 8 times greater than when you're sleeping. Okay? That's what this shows you. Did you guys understand that? Okay, so that's what that. So we'll see the difference between the anaerobic and the aerobic phase. The aerobic phase is you're breathing in, okay? And the anaerobic phase is when you're producing energy when you're not breathing in. And this is important when, let's say, you want to run away from danger and stuff like that. You want a sudden burst of energy, and you're not able to bring in enough oxygen. Okay, so how does that happen? Okay, to release energy from ATP, you need oxygen. Okay. So in the anaerobic phase, humans and other animals can work for short periods of time, and that's about a minute, at much higher rates than can be maintained for long periods of time. Okay, so this is, when you have to have a sudden burst of energy or running away from danger and stuff like that. This ability is useful in emergencies, allowing an animal to climb a tree very rapidly, run away, or fight fiercely when there is danger. To do this, the body rapidly oxidizes available blood sugar with oxygen already present in the body and makes the resultant energy available to vital organs and the skeletal muscles. The heart rate increases to circulate substances more rapidly to areas where they are needed. Blood flow patterns are altered to send more blood to organs active in stress response, such as skeletal muscles, and less to those not immediately needed, such as the skin. Okay. So all that happens very fast, and this whole entire thing will last about a minute. Okay. The spleen contracts to put stored blood into the general circulation, making more sugar available immediately. The liver transforms large amounts of stored glycogen into glucose and release it into the circulatory system. Glucose can be rapidly oxidized to obtain energy. So in the anaerobic phase, all these actions utilize oxygen already in the body. And the higher power output cannot last more than about a minute. So all this stuff happens for about a minute. And you'd better escape from that line trying to get you. Okay? This stage is called the anaerobic phase because no ingestion of oxygen is required. Yeah. The aerobic phase, the body quickly becomes oxygen deficient during the anaerobic phase and requires oxygen from the lungs to maintain its activity. It thus enters this aerobic phase. Okay. So a series of actions are initiated to make possible the long-term production of energy in the aerobic phase. These include sweat production. Why do you have to start producing sweat? Because that extra activity is going to generate more heat, and you don't want to increase your body temperature about 37 degrees. So you got to produce sweat so that when the sweat evaporates, it takes away the heat. Okay? To dissipate thermal energy, rapid breathing. Okay. Now you can't be oxygen deficient, so you have to breathe rapidly, and dilation of the air passageways. You guys remember from the very first chapter, if you want to increase flow rate, what you do is you increase the diameter of the tube. Okay, so to make fluid flow, you can increase the pressure. Okay, so this was the flow rate You don't have to remember this expression, I'm just writing it down. Pi r to the power 4, 8 eta length. Okay, this was the expression from the first chapter. Okay, and this is important in many cases. This is this is the flow rate of the fluid. You can increase the pressure difference. That's not feasible. The best way to control flow rate in fluids is to change the radius of the pipe. You want a bigger flow rate, bigger blood flow rate, you increase the radius of the pipe. You saw that you increase the radius of the blood vessel by 50%. You can increase the flow rate by 500%. So you want more oxygen coming into your bodies, you increase the radius of the bronchial tubes. Okay. So we need energy to do work. You get input energy by food. You use it to do either work, generate heat, or any energy that's not used is stored as fat. Okay. Okay, the last two slides go over the energy consumption of the liver and the spleen. Okay, so the liver and the spleen use 30% of your energy. Okay. And so the last two slides, this is not in the book, but I've added this. The liver uses the energy for all these stuff. Metabolism, detoxification. Okay. The liver detoxifies harmful substances, including drugs, alcohol, and metabolic waste. Protein synthesis, bile production, fat metabolism. So the liver processes nutrients absorbed from the digestive tract. It performs gluconeogenesis, that is producing glucose from non-carbohydrate sources. Carbohydrate sources are long chain glucoses that you just have to break them up, but from glycogenesis, storing glucose as glycogen, and glycogenolysis, breaking down glycogen into glucose. So liver is an energy intensive organ. Okay, and again, it doesn't do any mechanical work, but it's consuming energy. Okay, the spleen, though smaller and less metabolically active than the liver, still requires significant amount of energy. It helps in the immune response, blood filtration, and it's a reservoir for blood. Okay, you saw that in the anaerobic phase, when you want a burst of energy, the spleen will release a bunch of blood which has glucose and oxygen content. Okay. All right, sorry I had to